Hi everyone, this is week 7 and we will cover this week how to find increasing, decreasing intervals, how to find concave up-down intervals. Then we will talk about how to sketch the graphs of functions, and finally in the second part I will cover L'Hopital's rule and how to apply it for indeterminate forms. Okay, so let's start with the first example. In this first example, we want to find the critical points of the given function f, okay? And then we will search for increasing, decreasing intervals, and then we will decide if there is any local max and local minimum values. So let's solve one of these questions listed below. Okay, let's choose this one. X squared, x minus 1, x plus 2. Be careful, this is not f but f prime, okay? The first derivative is already given. That's why to find the critical points, all we need to do is to check where it is 0 or where it is undefined, right? Okay, so first derivative is 0 when if x is 0 or x is 1, right? And first derivative is undefined if x is minus 2. Right? Okay, these are the critical points for us. Critical points. Okay, and then to decide increasing, decreasing intervals, we need to construct a sign table by inserting these critical points. Okay, we have what? We have x equals minus 2, x equals 0, x equals 1, and we are searching for the increasing, decreasing intervals of f. That's why we need to search for the signs of the first derivative function. Why? Because, let me put a recall here for you. If first derivative is positive, then f is increasing over that interval. If first derivative is negative, then f is decreasing over that interval. Okay, so let's say this is minus infinity, this is plus infinity. Over this interval now, I am trying to decide the sign of the first derivative function. You can easily pick up some number from this interval. For example, x equals minus 3. You can insert it to here and decide whether the first derivative is a positive or is a negative value, right? Okay, let's insert minus 3, and all of you can compute that the first derivative takes positive value there, and over this interval you can try x equals minus 1 to see that the value of the first derivative function is negative. Over this interval it takes negative values, and over this interval from 1 to plus infinity, first derivative function takes positive values again. You can insert details like at minus 2, first derivative function is undefined. Double line means undefined. At 0 and 1, it becomes 0. So we insert that information like this. And then now we are ready to find out the increasing, decreasing intervals. If first derivative is positive, original function is increasing, right? If first derivative is negative, decreasing, decreasing, increasing. By just looking at this plus minus signs, we decide increasing, decreasing intervals like that. So from minus infinity to minus 2, your function is increasing. From 2 to minus 2 to 0, it is decreasing, right? 0 to 1 over this interval, decreasing. 1 to infinity, it is increasing. Okay. And then what we want to find? We also want to find local max and min values. Okay. So if you look at this shape of your function, like increasing then decreasing, then what happens here? And also here, decreasing then increasing. Here, right at this point, x equals minus 2, your function has a local. You can understand whether it is max or min by looking at the shape. It's a local max, right? And here, x equals 1 is a local minimum value of your function. That's how you decide increasing, decreasing intervals and local max min values, okay? So let's, I will leave the rest in this group as an exercise for you, you will just construct the sign table to answer all the questions. So let's move on to the next group. In this group, the question is similar. We will find increasing, decreasing intervals, and then local max min and absolute max min values. Okay, let's deal with 34. Okay, we will analyze g of x function, which is given as this one. Okay. First of all, we want to find the critical points to construct the sign table. So we need to take the first derivative to find out the critical points. This is a product function, so we will apply product rule to take the derivative. The derivative of the first expression times the second, plus first expression times the derivative of the second part. Second part is a square root function, so its derivative is taken like that, times the derivative of the insider part, right? Times minus 1 coming from the derivative of the insider part. Okay, this is your first derivative function, but in this form, it is not that easy to see where it is 0 or where it is undefined. To find out easily, we will write it over a common denominator. So we will expand this part with this expression so that we can write everything over a common denominator, right? Okay, it goes like expand the first term, so it will become like that, minus x squared divided by the common denominator like this. Okay, then you can write this in a more compact form, like 20x minus 5x squared divided by 2 times square root. Or you can even write it like in the most simple form like that. Okay, so in this compact form of the first derivative, it is easy to see where it is 0 or where it is undefined. First derivative function is 0 when x is 0 or x is 4. And first derivative function becomes undefined if x is 5. Okay, so these are the critical points. By the way, you also need to look at the domain of your function to understand which critical point we should take, which of them should be eliminated. So look at this line, please. We want to find the domain of your function g. You know, x squared is defined everywhere. So for the domain, you need to analyze square root function, right? Square root 5 minus x is defined when this insider part is greater than or equal to 0. So 5 is greater than or equal to x. So the domain of this function is this interval, x is less than or equal to 5, minus infinity to 5. 5 is a closed interval. Okay, this is your domain, and as you noticed, all the critical points are inside the domain, so they are all taken. If the case would be like one of them is not included the domain, you would eliminate it. Okay, now we have the critical points. We are ready to construct the sign table, right? Okay, insert all your critical points to your table. 0 in the increasing order, of course. First derivative, second derivative, the original function. By the way, after 5, we don't care what happens because look at the domain. Domain ends with 5. So after 5 is not included in the domain, so we don't analyze after 5 part. Okay, now the signs of the first derivative function. Before 0, this is your first derivative function. If you insert a negative value for x, pick any value like minus 1, you will see that it will get negative values. At 0, it is 0. Between 0 and 4, you can try 1. You can insert 1 for x and see that it start taking positive values. At 4, first derivative is 0, and between 4 and 5, first derivative function gets negative values. Now, by looking at these plus minus signs, you will say that first derivative, since first derivative is negative there, g is decreasing. increasing, decreasing. Okay. After putting these arrows, it is easy to see local max min values, right? Here, this kind of shape appears. So x equals 0 is a local minimum value. And here, increasing then decreasing, that's why x equals 4 is a local maximum value. So increasing, decreasing intervals and local max min values are like that. There is also another question, absolute extreme values. This means absolute max or minimum values. How do we find? We handle local max and local min by looking at the sign table. It is easy. But to find out absolute max min values, this is the topic of the previous weeks, you need to make a list of your critical points and endpoints, right? Okay, so let's make that list. X equals 0, x equals 4, x equals 5, and the domain endpoints you will need. Where is the domain? Domain is here, minus infinity to 5. 5 already appeared in the list as a critical point, so minus infinity. Since it is an open interval, you will look at the limit. At all those points, okay, this is a list of critical points plus the endpoints, right? Critical points, and this comes from the end point of the domain. Okay, for all these points, you will look at the image, the value of your function. G of 0, G of 4, G of 5. And of course, you cannot insert directly minus infinity. You will look at the limit. Limit as x goes to minus infinity, G of x. Okay, your G function, you know the expression for it. Here is your G function, x squared times square root 5 minus x. So you can easily compute these limits like 0, 16, 0, and also limit, let's compute it, is x squared 5 minus 8. What is this limit? What do you think? You are inserting infinity for minus infinity for x. So if this goes to minus infinity and this goes to minus infinity, so you can see that the result is plus infinity. Okay, now among all these points, you will choose the biggest and smallest to find out the absolute max and min. I think this is the smallest value, so you will name it as the absolute min. This is the biggest value, but it is not a finite number, right? You can never attain plus infinity. So there is no absolute maximum value for this function, as plus infinite can never be attained. No absolute max. Okay, I think I can draw a very general shape like graph to visualize all those things for you. Okay, our function g first. Okay, now I am looking at these signs, increasing, decreasing intervals. It is decreasing, then increasing, then decreasing, right? And at minus infinity, it gets plus infinite. This is for minus infinity x points, it gets plus infinite. And at x equals 0 and x equals 5, sorry, this is 5. This is at x equals 5. This is 4, I guess. Yes. At x equals 0 and 5, it gets its minimum value as 0, right? So that's why these are absolute max. Sorry, absolute mean, of course, not max. Absolute mean values. At the same time, they are both local means. Local mean, and there is this point attained at x equals 4. This is absolute max, okay? So I think this picture visualizes what happens here. Every absolute max and absolute mean is at the same time local max and local mean. By the way, yes, you're right. I cannot call it as absolute because it grows to infinity. You are right. No absolute max, but this part is a local max that we obtained in. Also, without looking at this visualization, the picture, you know, local max, local mean, also from this algebraic computation, you know everything, but I just draw it to show you a picture of this function. Okay? Any questions? So let's move on with the next example. Okay, our next example is now sketching the graph. We will use all those skills like finding increasing, decreasing intervals, finding concave up-down intervals, finding critical points, finding local max means. All those things will be needed to sketch the graph of this function. First of all, always you will start sketching graph questions with finding the domain of your function, okay? Look at this expression, x squared plus 4 over 2x. What is the domain of it? Every real number is valid except 1. You need to exclude 0 because the denominator cannot be 0. Okay, except the point 0, you can take any real points. This is the domain. Now, second thing is to find the critical points. To find the critical points, you need to compute first and second derivatives, right? And look at your function. It is x squared plus 4 over 2x. You can separate it like this. Then the derivative of the first term is 1 over 2. Derivative of the second term is minus 2 over x squared. These are easy derivatives. So this is your first derivative function. Now you can see that where it is 0 and where it is undefined. The first derivative function is 0 if x is 2 or minus 2. And the first derivative function is undefined if x is 0. Okay. If you are doing a solution for curve sketching question, you also need to compute the second derivative, okay? So by looking at here, you can easily compute the second derivative function. 1 over 2 is gone after taking the derivative. For this part, it is minus 2 times x to the power minus 2. If you take the derivative, it will become plus 4 times x to the power minus 3, right? Like this. So second derivative is computed like this. And then you also need to find the critical points of the second derivative function. We will need it to detect the concavity, okay? So let's see. Where this is 0, where second derivative function is undefined. It is never 0 as you have always 4 at denominator, so no point coming from here, but it is undefined when x equals 0. Okay, so let's see what we have. We computed these critical points. 2, minus 2, 0, 0 appeared once again for the second derivative. Now, behavior at the critical points means that find out local max and local min points, increasing, decreasing intervals, inflection points. By the way, what is an inflection point? Let's recall. These are the points where second derivative, maybe I should explain it like, where concavity changes, okay? Concavity changes. And I want to put one more recall here. Just like the first derivative, second derivative also gives us important information about the original function. Let's repeat this information. If the first derivative is 0, f is increasing. If the first derivative is, if the first derivative, not 0, sorry, I said 0. If the first derivative is positive, f is increasing. If the first derivative is negative, f is decreasing. And if the second derivative is positive, f is concave up, like concave up shape looks like this. If second derivative is negative, our f function is concave down, like this shape. So first derivative gives you information about increasing, decreasing. Second derivative gives you information about concavity. And about inflection point, what did I put here? Inflection point are the points where concavity changes. And concavity changes when the second derivative changes its sign, as you can see here. If it is positive, concave up. If it is negative, concave down. So concavity changes from up to down, down to up if second derivative changes its sign. So you can call inflection points are the points where second derivative changes its sign. Okay, so behavior at the critical points, increasing, decreasing intervals, concavity information, and inflection points. We can answer all those three parts at once by constructing a sign table. Okay, let's construct a sign table. Okay, what kind of points we have? We have -2, 0. You see, we already computed them here. I am now putting those critical points in my sign table. These are the points. Now I will look at the signs of the first and second derivative. Okay, first derivative function is here, x squared -4 divided by x squared. If you insert a point less than -3, for example, less than -2. By the way, let's also indicate that at -2 and +2, first derivative function is 0. At 0, it is undefined. At 0, second derivative function is also undefined. So now, before -2, first derivative gets positive values. Here, you can look at this expression. And if, for example, insert -3, you will see that it's positive. Between -2 and 0, it gets negative values. You can insert -1, for example, negative. And over this interval from 0 to 2, over here, it takes, you can insert 1 and see that it takes negative values again. And after 2, from 2 to plus infinity, it takes plus values. You can easily insert 3, for example. Now look at second derivative function. Second derivative function is here, 4 over x cubed. If x is positive, it is positive. If x is negative, it is negative, right? That's why if x is negative, it is negative. If x is positive, it is positive. Okay, like this. Now, looking at this table, we can say where f is increasing, where f is decreasing, right? Okay. Plus means f is increasing. Minus means decreasing. Minus, decreasing, plus increasing. You decide increasing, decreasing intervals like that. And by looking at the second row, the second derivative function row, you can decide whether it is concave down or concave up. If it is plus, concave up. If it is minus, concave down. Now, I will combine these two information. I have a concave down shape, and I also know that f is increasing. That's why I will take this increasing part of this concave down shape, okay? This part is the decreasing part, this part is the decreasing part, and increasing part. Okay, these curved arrows tells you the behavior of your function. We will be using these behaviors, curved arrows, while drawing the graph. Okay, now local max-min points. Is there any local max-min point? If first derivative changes its sign from positive to negative, negative to positive, there should be local max-min points. So you see there is this kind of shape here, increasing and decreasing. So x equals -2 is a local maximum point. And similarly here, at x equals 2, we have a local minimum point. Is there any inflection point according to this sign table? Remember, what's an inflection point? An inflection point is the point where concavity changes or where second derivative changes sign. There is such a point here. Second derivative changes sign from negative to positive at x equals 0. But you cannot take it as an inflection point because it is not included in the domain of your function. Remember, also your function f has double line at x equals 0. It is not in the domain. Okay, let me explain it here. X equals 0 is or cannot be taken as an inflection point. Cannot be taken as an inflection point because f, your function f, is not defined at x equals 0 because it has a double line there. Okay, this is the explanation about inflection point. So all those three parts, behavior at the critical points, increasing, decreasing intervals, concavity, and inflection points, are covered in this table. Now, asymptotes. This is another important part of curve sketching. We covered three different asymptote types, right? First, horizontal. How do we detect horizontal asymptote? We look at the limit of your function as x goes to plus or minus infinity. This is the function x squared plus 4 over 2x. Since the degree of the denominator is bigger, this limit is infinite. And we also take the limit as x goes to minus infinity. This time, it is again infinite, but minus infinite, because you are dividing plus with a minus quantity here. So minus infinity. Since we didn't obtain any finite value, there is no horizontal asymptote. Let's search for vertical asymptote now. To search for vertical asymptote, you look at your function and you try to find a point where it is undefined. Basically, you look at the denominator. So if there is a point where denominator is 0, then this line, this vertical line, is a candidate for vertical asymptote. But you cannot just say this is a vertical asymptote and move on. You need to look at limits around this point. Limits from left, limits from right. Okay, what I mean is you have to understand the behavior of your function around this point. This is very important. Without having this information, you cannot draw the graph, okay? So let's look at this one-sided limits around x equals 0. Okay, from right and left. So this is obviously infinite because you are putting 0 to the denominator. The question is whether it is a plus infinite or minus infinite. In the first case here, everything is positive. So this is a plus infinite, but here you are putting a negative value to the denominator, right? You are approaching from the left. So this is minus infinite. I warn you, please don't forget to compute these limits to understand what happens around vertical asymptote. Without this plus infinity, minus infinity information, without these limits, you cannot draw the graph because you will need this information. So what we obtain here is, if you approach 0 from left, your graph will look like this. It will diverge to minus infinity. If you approach 0 from right, your graph will behave like this, towards plus infinity. This is important. We can also indicate this information to our sign table because, I mean, the sign table should contain everything. At the end, we will just look at the sign table to draw the graph with all the information. So around 0, let me draw this line. Around 0 on the left, your function gets minus infinity. On the right, gets plus infinity. Also, at minus infinity and plus infinity in its domain, at minus infinity, your function, what was the limit as x goes to minus infinity? Sorry. I mean this part. As x goes to minus infinity, your function is minus infinity. As around plus infinity, your function is plus infinity. Let's also indicate this information to our sign table. So here at minus infinity, the values are minus infinity. At plus infinity, the values of your function is plus infinity. Okay, we put those information to the table. There is one more asymptote type, which is oblique asymptote. And this happens when the degree of the denominator function is one more than the degree of the denominator function, denominator polynomial, right? Okay, let me write again. F of x is x squared plus 4 over 2x. Look at the degree here. It is 2. And look at the degree at the denominator. It is 1. Degree of the polynomial. If degree of the nominator function, let's call it as px, is degree of the denominator function, let's call it qx plus 1, this holds for us. Then there is an oblique asymptote. Oblique asymptote. And how to compute that? you perform polynomial division to find out the oblique asymptote equation. So x squared plus 4, I am doing this polynomial division, honestly. So x over 2, we should multiply it, and this becomes x squared, take the difference, 4. Division is over, and what you find here will be your oblique asymptote line. Okay? Y equals x over 2. This is a line, and it is oblique asymptote line for us. We have one vertical asymptote, which is x equals 0, and one oblique asymptote, which is y equals x over 2. Okay, after handling the asymptotes like that, there are 3 kinds of asymptotes. Then now we can start drawing the graph. And I took this graph from your course book, but don't worry, we will draw it together. Okay. First of all, you have to insert asymptotes to your Cartesian coordinate. We have this asymptote, right? Y equals x over 2. This is the oblique asymptote. There is another asymptote, which is a vertical one, x equals 0, which is the y-axis, right? Okay, I first inserted the asymptotes. Next, you can start drawing your graph. Okay, now you need to look at the sign table. Over this interval from minus infinity to minus 2, I will draw such a shape. Remember, we obtained that shape. Then, after x equals minus 2, I will use this shape. And around 0, as 0 is the vertical asymptote, I will send my graph to minus infinity. Let's do that. Okay, increasing, decreasing, then on the left side of 0, it will diverge to 0. Okay, maybe it is better that I draw this again. Okay, y equals x over 2. This is the oblique asymptote. What does it mean that you have an oblique asymptote? It means that around minus infinity and plus infinity, your function behaves like this oblique asymptote. That's why I start around this line, oblique asymptote line. Then our graph is an increasing graph till which point? Till this point at x equals minus 2. Then remember the curved arrows. Then it decreases. And what happens around left side of the origin? Your function diverges to minus infinity. You see, I used all that information. This was the vertical asymptote. Okay, you see the graph over this interval from minus infinity to 0 over here. We draw this graph by adding one another that curved arrows that we obtain in the sign table. Okay, then what happens on the left side of 0? Remember, I warned you about that part. On the left side of 0, your function gets plus infinity, because it's x equals 0 is a vertical asymptote, remember? So I will start drawing at the plus infinity on the right side of 0. Then what happens? Let's look at the sign table. So I start at plus infinity, and I will use this arrow till 2. And after 2, I will use this arrow so that there will be a local minimum at 2. And at plus infinity, the values of my function will grow to plus infinity. So let's draw it. Over 0 to 2, it will decrease. And on the left side of 0, I start drawing the graph at plus infinity, as it is the vertical asymptote. Let's say this is the point 2. Okay, and then my function will be increasing, and it will behave like our oblique asymptote at around x goes to plus infinity, like this. So that's the graph. Any questions? Okay, so let's just go over the steps once more. First of all, the first step is always finding the domain. And then you will compute first derivative, second derivative, critical points of them, because you need them to construct your sine table. Then these three steps are handled at once at the sine table: increasing, decreasing intervals, concave up-down intervals, local maximum, critical points. All those things can be seen at the sine table. And then there is also another important step here: asymptotes. You will search for all three types of asymptotes. Sometimes one of them doesn't appear, sometimes none of the asymptotes appear. You will just check them. And then you will start drawing the graph. First of all, you need to draw the asymptotes. And then by looking at the curved arrows in your sine table at the last row, like this one, you will start drawing things. So that's it. Any questions? Okay, let me draw one more graph for you before we take the break, and then we will take the break. This time, our function is this one, e to the power 2 over x. We will first, always, as usual, start by finding the domain. Look at here, e to the power 2 over x. 2 over x is a rational function, ratio, so you cannot put 0 to the denominator. That's why you can take all the real numbers except 0. This is the domain. And then what we usually do, we compute first and second derivatives. How do you take the derivative of e to the power something function? It is, the rule for exponential is itself times the derivative of the power, and this derivative is in fact minus 2 over x squared, as it is written here. And you can write it like this. Next, you will find the critical points by searching like where f prime is 0 and where f prime is undefined. E to the power function is always a positive function. It never gets 0 value, okay? That's why there is no point coming from here, no point. But it is undefined when x equals 0. Then, this is a rational, the quotient function. That's why you will apply quotient rule to take one more derivative to obtain the second derivative of your function. It goes like, okay, derivative of the numerator. This is the derivative of e to the 2 times e to the power 2 over x times the denominator minus numerator stays the same times the derivative of the denominator divided by the square of the denominator. So you can take the derivative one more time by applying quotient rule. So if you write it in a compact form, you will obtain this. Again, search for where the second derivative function is 0 and where it is undefined. It is 0 when x is minus 1, and it is undefined when x is 0. So these are all the critical points for us. Now we are ready to draw this sine table together. Okay, let's do that. Insert your points to your sine table, minus 1, 0, and then first derivative, second derivative, then the function itself. Okay, before minus 1, look at your first derivative function. Here, e to the power x over 2 and x squared is always positive. But you need to be careful about this minus sign. Because of this minus sign in front, your first derivative function is always negative. Okay? It is undefined at 0. Let's put double line here. Also, second derivative function is undefined at 0, double line. It is 0 at minus 1. Look at the signs of the second derivative function. This part and this part is always positive. That's why to understand the sign of it, you will just look at x plus 1. If x is less than minus 1, you will obtain negative values. If x is more than minus 1, bigger than minus 1, of course, you will obtain positive values. This is our sine table. Now, looking at the sine table, we can decide increasing, decreasing intervals, minus, minus, minus. That's why our function will be decreasing always. Look at the second row. Minus means concave down, plus means up, plus means concave up. Now, I will combine these two information. Decreasing part decreasing part, decreasing part. Okay. Is there any local max min values? Let's see. First derivative never changes sign, always decreasing. So you will never have local max min values. But if you look at the second row of second derivative function, you will see that here at x equals -1, concavity changes, right? Second derivative changes its sign. So, yes, this point is an inflection point. No local max, but there is one inflection point here. Now, what is the next step? Without searching for asymptotes, you cannot draw the graph. So let's divide into steps. Let's say finding the domain is the first step. Second, let's say one. Second part, computing these two to find the critical points. Third part, constructing a sign table, searching for increasing, decreasing intervals, concave up-down intervals, local max mins and inflection points. We have an inflection point here. And let's say third part is the asymptotes part. We will search for all these three types of asymptotes. First, vertical asymptotes. Let's start with horizontal. Let's see if we have any horizontal asymptotes or not. So how do you detect them? You will look at the limit of your function as x goes to plus or minus infinity. This is the function. We will look at these two limits. Okay. So the result of this limit is 2 over infinite is in fact 0, right? So 1. Again, minus infinite. 2 over minus infinite is also 0. Nothing changed. 1. So since we have a finite result from these limits, you can now call y equals 1 line as a horizontal asymptote. Okay. Second, vertical asymptote. To detect a candidate for vertical asymptote, you will search for any denominators, like your function becomes undefined. F of x is given as 2 to the power 2 over x. So from here, you see that x equals 0 makes your function undefined. So this is a candidate. Why I am saying candidate? Okay, it is a vertical asymptote, but you should look at the limits around these points. You have to understand the behavior of your function around 0. You cannot pass to the next step without computing these limits. Please don't forget to cover these limits. Okay, what do we have? E to the power 2 over 0 from right. 2 over 0 is infinite. So e to the power is infinite is infinite. Second case, 2 over 0, but from the negative direction, right? From negative numbers. The first case was from positive numbers. So from negative numbers, it is again infinite, but since we are approaching from negative numbers, it is minus infinite. This is e to the power infinite, 1 over infinite, 0. Okay, these two limits will be used. Next, oblique asymptote. Is there an oblique asymptote here? As your function is not something like polynomial over polynomial, you can directly say that no oblique asymptote. Okay, so let's indicate this vertical asymptote and horizontal asymptote information with all those limits to our sign table. As x goes to infinity and minus infinity, your function approaches to the value 1. Okay, let's put that. Minus infinity plus infinity, your function approaches to the value 1 and 1. Around 0, what happens? On the left part, it is 0. On the right part, it is infinite. So I find 0 in my table. On the left part, it is 0. On the right part, it is infinite. Okay. Now, this table includes all the information we need. By looking at this table now, we are ready to draw the graph. Okay. First of all, indicate the draw the asymptotes in your table, okay? Okay, like that. This is y equals 1 line. Horizontal asymptote. We also have another asymptote, this one, right? X equals 0, which is the vertical asymptote. Let me also use colors for this horizontal asymptote, like that. Okay, I put the asymptotes first in my table. Now, I think before drawing the graph, you can just insert information about how your function behaves around asymptotes. For example, on the left part and right part, on the right of 0, we have infinite. On the left, we have 0. Let's also put this. On the left, we have infinite. On the right, your function will approach to 0 like that. I don't know the graph yet, but I am just putting the information. And horizontal asymptote means that your graph should behave like the horizontal asymptote around minus infinity and plus infinity. Now, I will combine all the information to complete this graph. Okay, now I am starting with minus infinity. As x is around minus infinity, our function will be very close to horizontal asymptote. Then look at the curved arrows now. We will use them. From over this interval from minus infinity to minus 1, I will use this arrow decreasing. And after 1, it will keep decreasing, but the concavity will change. So let's use them. And also around on the left part of 0, our function will converge to 0 value. Okay, let's do that. So it will be decreasing with this curved arrow. Then it will keep decreasing like that, but it will change its concavity. You see here, our function changed the concavity, and it will approach to 0. I cannot put a dotted point at the origin because 0 is not in the domain. Remember? 0 is excluded from the domain of our function here. So at 0, your function is not defined. That's why there is a hole there. Okay, after 0, remember, we put this information here. On the right part, the limit of your function is plus infinite. Now, I don't know how to draw the graph. I need to look at the sign table. After 0 to infinity, it will keep decreasing, okay? Like that. And around plus infinity, it will converge to your horizontal asymptote line. So we know how to draw it. Keep decreasing, and it will converge. You know, I already put this information. I just combine them as a decreasing graph, like this. Okay, the graph of this function looks like that. It has a horizontal asymptote, y equals 1. It has a vertical asymptote, x equals 0. And don't forget, you first need to draw the asymptotes. You need to understand how your function behave around the asymptotes, like here, 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 here. And then by combining those curved arrows in your sign table, you can easily draw the graph. There is an inflection point. Let's also indicate that. Inflection point is the point where the concavity changes. Okay. Any question about this graph? This graph, I have a question. Is there any absolute max? If you look at this part, you will see that no absolute maximum value is attained because it is infinite, never attained. Is there an absolute mean? Now you need to look at this point. Okay, 0 seems like the lower bound, but it is again not attained. It's a hole. So again, no absolute mean. It is not attained. You should be careful about those things. Okay, let's stop here.